So I think we are recording this now, which should be indicated to you in a red blinking dot. And then I am beginning to proceed forward in checking my handwriting here. And okay, the pen width and all that. So the topic that we will discuss today is reinforcement learning. As I already mentioned a little bit briefly, it is quite complex from a mathematics point of view, but that should not bother us too much because we handled the aspects of this program comfortably. I would say, we have had no big issues as such in terms of seriously getting stuck on understanding the math. That doesn't prevent us from going forward with accomplishing the understanding of what this thing is and how do we apply that piece. I think we can still move forward, even though sometimes the math can be a little complex to be handled in a video conference based boot camp. It requires thorough understanding of and reading multiple research papers, going through a deeper understanding in each and every field. Each and every topic needs its own domain of study. And so that's the nature of the beast here. Now, we know about this thing called, in 2013, there is this company called DeepMind, which I think, what happened to the pen here? Okay, this company called DeepMind, which was acquired by Google, they established that they can play the game of Go better than the best. The best person who's the world champion, his name is KG. I don't know how to pronounce that name right, but he is the world champion. He is the human champion, I should say. Human champion of the game of Go. And they came around and built a system that beat this guy. And I said, this guy lost. The system called, I think I need to go back to disabling touch. So let me just adjust that. And disable the touch feature. Okay. And so now this person lost at the machine called DeepMind. It's called AlphaGo, actually. AlphaGo. That was the game. And that was something that, eventually led to about, $500 million acquisition of this company by Google. And so they're now a part of the Google company, actually Alphabet company, I should say. And so that's this story. This was 2017 timeframe, pretty much last year. That was a remarkable feat. In that this is a game of Go as opposed to the other things that we have seen in the past, like IBM's machines play chess. This is a different scenario, a different type of game, and this. By the way, this company has further went ahead to generalize the same technique, and they can play any visual game, any visual game, which you can provide it a series of inputs in terms of screenshots. And so any action game, actually say action, any action-based like shooting guns or moving objects or playing around in Pac-Man motion or any kind of visual action-oriented game which has screen-based activity, and you have some kind of a joystick. So a classic example will be Atari games, Atari-based, the old machine that people used to play. Some of us still have it. So that gaming console, we had a screen and some kind of a joystick to move around objects. And we know already of the company here established a setup in which you feed the input, which are basically screenshots of the screen itself on the Atari platform, for example. And the algorithm was such that it will take an input. It will, based on this input, it will see that there is a goal or a score or a result in form of a reward that is being calculated, and what the machine needs to do, this machine, like the player machine. The player machine needs to provide action. So it looks at certain incoming images, series of images that are getting fed from the Atari system. And the player machine is able to take actions on the joystick. And as a consequence, maximize the reward. That's the goal for this machine, the player, that they want to maximize this reward, the goal, the score, whatever the leaderboard that we have. So the optimization at the top level is basically happening around the reward. I want to maximize this idea. And as a consequence of that maximization, I need to figure out what movements do I make. Do I move my joystick this way, that way, this way, that way, or a variety of motions you can actually have. And so if you look at a classic Pac-Man game, the Pac-Man game, there are various motions you can do. The item that moves around, eating things, as it goes. It can stay put and do nothing. It can, move this direction, or it can turn the face this direction and then move this direction. It can turn the face this direction. So basically there are 9 such orientations, 9 such moves that a Pac-Man unit can take in each of the sides that it moves around in, and we'll see exactly what we're talking about. And so those are the actions that the Pac-Man player machine needs to take. Similarly, there is a simple idea that I think we've discussed briefly, as this idea of a cart pole. A cart pole is basically just a pole. This pole is dangling in the air. So it is free to move around this direction or that direction. And it is mounted on a thing. There's a hinge here and there's an axis. So this axis that you have, that you look at, maybe look at this axis like this. And so this is the motion that the pole can go around this direction or that direction. It cannot go this direction. And all it can do is it can fall in this direction or fall in that direction on this plane like that. It can fall in either directions due to gravitational force. And it can be traveled across in this axis or that direction by physically moving this point towards this or that. That's the idea of a cart pole. Think of this pole mounted on a cart sitting on this line is able to travel this way or that way. And what we are really doing is trying to balance the pole in the air. The pole is not connected to anything else. It's not connected in this direction. Not connected. And so the idea is that a human can take this object, the cart pole, put the hand right here, human hand, and attempt to balance the pole. Many people are successfully able to do that effortlessly. Just take a pole, put in their hand, and you can have the pole balance on the hand itself, like on the palm of the hand. People are effortlessly able to do that. Some people do it even with small objects, even though it is kind of tricky, but they have trained themselves in managing and somehow balancing the cart pole. If we look at the cart pole from a machine's standpoint, so imagine this is the line where the pole is standing, and what the machine needs to do is take this action, whether the only action the machine can take, and maybe a human hand can also do the same action, is either move it this direction, accelerate in this direction, or accelerate in that direction. That's the only 2 actions you have to do in order to balance the cart pole. Only 2 choices. Either you go this way, let's call it the left choice, or you go this way, the right choice. And the pole itself is giving you some input observations. The observations that are being available to us, or rather the machine, I should say the machine player, This machine player is getting some input in terms of observations. It is observing the pole itself and is able to find out four things. The four things are, where is the pole? So this is think of it as an x-axis. So the pole can be at some point here. So that's the position. The pole itself, the point itself may be moving in that direction with a given velocity. So that is the velocity. The pole may be tilted a little bit like that and may not be exactly vertical. And so that is the, excuse me, give me a second. The pole may be tilted a little bit, and that is the angle. That angle is another observation. And the pole may be rotating or falling at an angular velocity of how many radians per second, what may be the velocity of that pole at that point in terms of it falling down from the top, going this way, radially going this way. And that's the fourth measurement, angular velocity. So these are the four things. So let's call them, 1, 2, 3, 4. 4 things to observe for the machine. And the machine can play only 2 things. You can either push the cart pole this direction or that direction. That's the decision the machine needs to make in order for the machine to balance the pole upright eventually. The input that it is getting is this. The decision is right here. And our ultimate result, or what I would say, the reward, is very simple. Is that the pole should not fall. That's it. That's the reward. So from a reward point of view, the pole should be standing upright on the line x-axis and should be upright. And the machine can move it this direction or that direction. That's the decision the machine needs to make, to push it towards left or to push it towards right. That's the decision. The observations. So there are these three things, 3 classes of information that we are dealing with here. One is the observation as the primary input. The action the machine takes, which is this action, left or right action. And the result, the reward, the goal is to maximize or stabilize or some kind of accomplishment, which is right there. That's the reward. And so if you want to generalize these ideas in form of any gameplay by a machine, and I'm generally calling it a gameplay, it can be applied to anything that is that involves some action, some decisions based on some input that you observe, and with a goal of maximizing something or stabilizing something or accomplishing some result. So ultimately, you maximize the reward by taking action based on observation. So you observe something and you take an action with the intention to maximize the reward. That's the underlying game. The whole game is this. This is the goal, this is the action you take, and this is what you see. The challenge in most games like this, or most activities where this thing is going to be happening by a machine player, let's call it machine player, the machine that plays. The challenge is that this reward is not immediate. When you have a pole like this and you see that it is falling this way a little bit, then the natural right course of action for the machine player is to push this direction. And so that will counter the falling force. By pushing it this way, it will attempt to go the other direction just by the nature of physics. Similarly, if the object or the cart pole is falling this direction, the natural correct course of action to balance is to push the pole this direction and thereby attempting to balance. However, the problem is that the immediate result is not correctly and always an indicator of the final reward that you will get. Meaning, you might actually take a course of action this way and push it that direction heavily. As a consequence, you might see that the object goes this way, and sometimes if the force is too large, it might actually go all the way in the wrong direction, and thereby diminishing the reward. And so your immediate result is not necessarily indicative of the reward you will eventually accumulate after a series of actions. So you take this action, you take that action, you take this action, you take that action, and you try to balance it a little bit. Eventually, you will find it after some time or some attempts that you might see the pole correctly balancing, and you will keep on balancing it because the fall or the angle is a little bit tiny. So the forces that you apply are also tiny, and they are effectively counterbalancing and making sure that the pole is all upright. And so the challenge that you see in most real life examples is that this reward is not almost immediate. It may be there after a couple of attempts, after a couple of actions. So anytime you want to take an action, you have to actually foresee what will happen eventually after a series of actions, which is kind of mathematically challenging in a sense that you don't know what you should do right now, because right now if you take some action, it might actually attempt to minimize the reward as opposed to maximizing it. And that may be a wrong thing to do, but maybe there's a case in which we have to understand how do you apply these techniques to ultimately maximize the reward that you want to accomplish. Like for a game of, a board game of some kind, some Atari game or some, game of chess, game of any type. You want to ultimately accomplish a win or maximize the points that you accumulate. Or in Pac-Man, for example, you want to basically get the highest possible score. And so you don't immediately get to make that clear understanding by an action that you take on the Pac-Man thing. I don't know what it's called, MS Pac-Man. This thing, whether its face should be this direction, this direction, this direction, or that direction, and what direction should it be moving. And that action is not super apparent in terms of whether a particular action will actually maximize our reward in the long run, in the entirety of the gameplay. And that's the relationship which is not immediate. That's a challenge. And for this, there is this math which comes into play called Markov decision process. And so we will discuss that a little bit, Markov chains and Markov decision process. And so we'll see that's where the math comes into play, and its expansions and extensions and variations that you will see as we go and apply. So there are these techniques which are the culmination of this entire chapter. You will see that they basically are able to help us understand two broad techniques. One of them is the policy gradient, and the other one is called Q learning. And then you have
the red marker doesn't show up very well. Could you switch to?
I see what you're saying. Okay. I see. Okay. Yeah. Okay. I think this should be good. Yes. Is it good?
That's a lot better.
I can make it bigger if you like.
That's good. Either way is fine. I can see it's a lot more clear.
Okay. Yeah, that was too thin, a little bit thin. So I think this is good. Okay. So the two broad categories of algorithms that we will discuss are basically around policy gradient, and the other one being Q learning. And we apply deep learning techniques to this deep neural network. So it becomes DQN effectively. And so that's what you will see are the two examples of algorithms that are described in, there are some very fabulously detailed applications and coded examples that you will see in the notebook corresponding to this. And to run that notebook, it might take like a couple of weeks to eventually run, but it will run. And the idea will be that it will actually help you play the Pac-Man game. Not help you play, but the machine will play Pac-Man for you, as opposed to you playing Pac-Man. So that's the difference here. So machine will play Pac-Man. You will see the machine play cart pole, and that simulation of the cart pole moving around left and right, and the machine player trying to balance it out. You will see live video implementation based on the code you will see running in that notebook. That is actually very, very interesting because there are real life applications right there. Give me a second. I'll need to grab a piece of paper. Hold on. Away from me. Yeah, I think I'm back. So put my microphone back in place. So let's go begin looking at these ideas, which will help us understand these two techniques, and we proceed forward. So that's what you will see, policy gradient and DQ networks. And this can be applied to anything that you want to accomplish, like a self-driving car. You have the creepy robots that you look at, Sophia, for example. You have the not so creepy robots doing what was that, Boston robot, Boston Dynamics. It is a nice looking thing that you should see. You may have seen it, Boston Dynamics, Bruno Mars. That's fascinating. Bruno Mars, there you should see that. If you haven't seen this, that's the video. It's a very recent video. You should watch that. It is actually fancy, beautiful footwork by the robot in terms of making that dance, which is how it is challenging Bruno Mars in this video. You take a look at that, definitely. It is actually fascinating. Having said that's what we'll discuss. Not the Bruno Mars dance, but the concept underneath that. So here, optimize. The concept of optimization here involves the thing that we have some observations coming in. We want to ultimately maximize the reward, and we have to take actions. The actions can be any set of motion, movement, decision, some corrective step, or something that basically is an action of the machine player. And the observation is what what the machine player sees, and ultimately maximize the reward. That's what you have to maximize this all the way. So let's see what we can apply the same concept here to a variety of games. It can be, like I mentioned already, Pac-Man like games, the game of Go, thermostat. That I think that's a very, very, just like right now, I have an example of a thermostat that you should see. It's a real life example that I just witnessed today, and that I think is very relevant. So I will just show it to you. This is a thermostat installed in my home. I'm going to log in and show it to you real life what it just did, which was fascinating to say the least. And so you will see that here I'm logging in. It is loading my thermostat data. And excuse me. In here, what you will see is that I have some sensors. And let's see what sensors I have. So there is a sensor called thermostat. There is a sensor called, let me get my highlighter here. Yeah, so there is a thermostat, which is the main unit. This is the main unit. There is a thermostat sensor in the bedroom. There is a sensor in the living room. There is a sensor in my office. And so, as you can notice, the temperatures in various rooms are different. So the underlying logic behind this thing, Ecobee, is basically what we are discussing right now. It has these inputs or observations that it has. It takes from these sensors. That's the observations. It gets these observations collected from here, and it takes actions. The actions taken right now in winter are very simple. That action is actually quite basically it's a switch on off. That's the only switch. So in winter time frame, the only thing that it can control is furnace or the heater. Furnace on or off. That's the decision, the action it can take. The observation is from sensors. And what's the goal? The reward, the goal. So let's look at the goal also. I will now show you the goal idea here in the context of what the goal is. So goal is what I have set, is right here. And that goal in my example happens to be this. That's the target temperature. Sorry, no, this is not the goal. This is the desired, the target value. And there are two ideas here: the actual value and the desired value. So that's the target here. So I can adjust this. I can manually move it up and down if I like. And I have today set a little higher until 9 p.m. So set this my desire. And that becomes the goal, the reward. Now what it has accomplished, almost accomplished by now, is that it has this result. So this is the resulting temperature. This actually is calculated based on averages, average in multiple rooms. So there are sensors in various rooms. So it basically does a quick mathematical average. So there are 4 values, A, B, C, D. You sum them up, divide by 4. That's what this number is. And it tries to accomplish the desire. The resulting temperature will match the desire. That's the goal of the system. And there is one more hidden goal, which is not super obvious, is that the system is given negative points anytime I need to go and adjust this manually. Anytime it is me who's like going to adjust this setting and move the circle up, let's say manually move this thing like that direction or maybe this direction, then the system is given a negative reward because human needed. And so the idea is that this is a smart system. It should be able to predict what my need is based on my weather outside and the actual temperature inside and my desire mentioned that I have called out, by the way, in my schedule. So every day, whatever duration, whether I'm home, I'm away, or I am on vacation, or or whether it is nighttime or daytime, or things like that. I have told it my desire already once, and the system should be smart enough to look at the temperature here outside and look at the sensory data and automatically self-adjust. So that's the setup of the discussion. Now comes the point of discussion. The point of discussion that I want to have today is to illustrate the idea where this thing is able to accommodate and adjust itself based on something crazy that I did today. What did I do? I bought a heater, a room heater that just focuses on one room heater. And I placed that in my room, in the studio, in the home. So where the program runs from the boot camp, the video camera and lighting and all that. So I was here in the morning in the studio, and I put this room heater in that room, and I was feeling cold, so I actually pumped it up all the way to 80 in just that one room. So what happened is, as a consequence, the input calculations were thrown off. This was a new entry into the home. And so this set of sensors, the studio that you show 75, was actually showing you 82 a little while ago. And as a consequence, the system got confused, because you see the number 82 here. And so the overall average of these numbers was actually higher than the number 73 mentioned. And so the heater was off. The furnace was off, because the math shows that your actual temperature is more than desired temperature, because this is the actual average of 4. And so the actual went higher than desired. So the furnace was off for a long time. And as a consequence, what I noticed is that these temperatures went all the way down to like 62, 63, like something like that. And this one was heating up. And so it went all the way to 84, 85. And it was hot in this room. And as a consequence, the heater was off. The home was cooling like crazy. So my wife is complaining, why is it so cold? And it is because of this somewhat overheating in my room. And the system was smart enough to pick that up based on aggregation of 4 different sensors, and conveniently and probably mathematically correctly deciding that the actual average temperature in the home is actually more than the desire. So I should keep the furnace off. So then when my wife complained, I actually moved the sensor out of the room. And as soon as I move it out, this sensor was physically relocated out of the studio to another room. The other room is cold. So all these temperatures are cold. I mean, they're like 63 or so. And this was 84. And so I moved this unit, the sensory equipment, outside this studio into another room. And suddenly this becomes on, because the actual average drops down to below 73. And then, it picks up the idea that it needs to trigger it up. The goal of this, the point of this discussion is that this system is actually doing exactly what we are going to discuss today, which is the idea that is just one more example of application of this technique, which is you have an observation to make, you take actions based on observations you see, but the ultimate goal is to eventually accomplish some reward, which is to not bother the human in setting up the right temperature for the home, or to accomplish a target temperature, or things like that. That's for the thermostat. Excuse me. So that's here, smart thermostat happening, getting rewards wherever it goes closer to the target temperature, saves energy. So it did save energy for me. And whenever human needs to tweak the temperature, and that's when, it failed. So it got a negative reward as a consequence, and it reduced the reward. So that's when it probably attempted to learn a little bit on its own. So that's a system in play for real in this example. So this is an example of something that is not actually a physical action. It's more of a electrical on-off switch, as opposed to some motion of a physical object like a cart pole or a Pac-Man or something like that. You can apply the same concepts to stock market, but that is something that, I don't like the idea of investing like this. So that's crazy. But there are, by the way, machines in the stock market today that look at intraday, second-to-second pricing, and are able to make a buy-sell decision based on how the stock market is reacting based on news that you collect.
based on historical stock prices, based on other events happening in the market for similar stocks. And on a second to second basis, you can find that there are systems that are trading and potentially making monetary gains and losses. These are day trading machines. So we have equipment like that, day trading. Day trade. There are people who do day trading manually. These are humans doing it, but there are day trading machines. These things are called high frequency trading. And these are basically computers looking at techniques like mentioned in this chapter, apply that to placing trades as an action. So you make an observation, can be from the stock market movement of a particular stock or a given set of stocks. There can be news coming in, the ticker price of a particular stock, news around that, and then you take an action called buy or sell or something like that. And then, or maybe there is another action called do nothing action. That's another action. There are, by the way, a couple more actions in the stock market you can do, not just buy, not just sell, and not just do nothing. There are two more actions which you can classify as take a call option, take a put option, or you buy, call, buy, or buy or sell call, buy or sell put, or a combination of that. So there are a variety of actions you can actually take in the stock market, not just simply buy or sell or do nothing, but you can buy a call option, sell a call option, buy a put option, sell a put option, and any combination of all these things. So lots of different actions a potential trader can take. And that's where the application of this comes into play. Excuse me. I think I'm catching cold or something. So let's go forward here. And we'll now take a look at some example applications. I think I just mentioned I have this ecobee unit that I was showing you, the game of Go, the Pac-Man game, stock market, and the Boston Robotics Dynamics robot, which is the walking robot. It's now a dancing robot. That's what I think. You should watch the video. You will like it. Now, sometimes the goal that we have, the reward that we accomplish, may not be always just positive, negative, maximize. That may not be the only game in town. Sometimes the goal is to not actually get a positive reward, but to get out of something like a maze, for example. And so there is nothing much to gain as such, but the goal in that maze, if you're in a maze, the goal is to quickly exit as quickly as possible. So fastest route to get out of the maze. That's the game right there. And so the goal is to just the time it takes, time to exit the maze, and you want to minimize that time. And so the goal is different. But again, in a maze, you are walking around and you need to figure out, without spending too much time, the least amount of time, how do you quickly exit? And that's the idea in case of a maze. There are other examples of self-driving cars. There are examples of placing advertising on a page. This, by the way, is a very delicate and highly debated subject these days. That's where, question of maximizing. The goal here is placing ad placement is what is done by Google. And Google places an ad onto some publication, right? Publication is something like a magazine, CNN.com, FoxNews.com. These are magazines, publications. And there are people who publish. They're called publishers. And these are the magazines that they publish. What Google is doing is taking an ad from an advertiser, taking it from the advertiser, and basically placing it on a publication. And what they are really trying to accomplish, so this is the action of an advertiser, taking an action to publish an ad and selecting the target publications. That's one action by the advertiser. The other action that Google is doing is basically selecting appropriate ads from various advertisers coming into Google system, advertiser number 2, advertiser number 3, and publication number 1, publication number 2, publication number 3. They're optimizing which ads should go to which publications at what time, and that's the action Google is taking with a goal of maximizing what? Maximizing free speech? Not exactly. They're maximizing their ad revenue. So that's what Google is in the business of. That's the primary business. By the way, this is the business of Google, the business of Facebook, the business of any of the free social media channels. That is their goal right there, is to maximize the money they make by placing advertisements from various advertisers onto various publications. Sometimes they are the publication themselves. Sometimes they are the platform on which other people publish. And so, like you and me, people like us, will post pictures or some other messages on the platform that these guys provide, like Facebook, Google, Twitter, LinkedIn, bunch of other, Instagram or God knows who. So they are basically maximizing their advertisement revenue. They're not helping us in doing anything, whatever we think of them as, but they're helping themselves in maximizing their ad revenue. So that's where this thing is coming to play. Placing ads on a web page. Now, the way it is described here is kind of trivial. Excuse me. The way this is described, like placing ad on a page, is very trivially written right there. But the more complex idea is to actually maximize ad revenue coming in for a potential, no, not potential, for a platform. A platform in which there are publications that provide content. There are advertisers that provide ads. And what these companies are trying to accomplish is basically maximize the money they make. So that's the goal right there. Oh, I think I cleared it up by accident to choose that. And they're trying to maximize this money. And people like you, me, public, they're also putting content in there, like put a picture on Facebook platform, for example. And so Facebook is, of course, optimizing the money. They're not into, deciding, whether it's a Republican or a Democrat story, or, whether it's, A versus B story, or free speech or suppression of free speech, pornography or not pornography, or any kind of sort of topics that people discuss. They're not into that. They don't care, honestly. All they care about is their money. And so that's what they're trying to optimize. And that's where, the same game applies. You have the company, Facebook, Google, all those basically ad money makers. They look at your input, like the sensors that collect data about, where the publications are, where the ads are, and then find out what actions they take, which ad should go to which place, which direction, which location, and how do you curate the platform, which news feeds come on top, which news feeds get suppressed, or hidden behind, left behind, or ignored. And how do we essentially take those actions based on observations to maximize the reward, which is the money they make. That's the whole game. It's a big thing that, this technique is applied right there. You will see, controlling an image classification system should focus his attention. So, self-driving cars. There are new cars, by the way, announced, I think just a couple of days ago. I saw news about a new company called Rivian. This thing is starting to take pre-orders. It's an electric truck company. There are more such companies coming up these days, and everybody is trying to claim the game that Tesla started. And people are just building new stuff. These things are going to apply the same things that we are discussing right now. And so the underlying concept is like this. You have the agent, which is I call it the machine player. The entity or the software that is actually playing the game. This is the agent. So the agent is looking at some observations. He's taking actions and is accomplishing a plus or a minus reward. It can be either way. The reward can be positive, like this, or negative, like this. So you get fire. So you walk in the wrong direction. So you start walking, you walk in this direction, there is fire here. And you walk in that direction, there is green grass here. And so that is a good thing. You can walk on the grass all day long, and that's maybe pleasure. You walk on fire, that's probably negative. And so you have the rewards right there. Reward, another reward. And the action to take is walk this direction versus walk that direction. And so this idea of fire showing you is the idea of showing you a negative reward. And here is your positive reward as water. So that's the environment observation. So that's the observation taken in. You make a policy decision, and based on that policy, you take an action. Now the question is, what's the right policy? And how should we go about deciding what should the action be? Because there are like so many different possible combinations of an action you can take as you walk in an area where you're standing right here, and you can go this way, that way, or just about any direction, right? Any arbitrary direction you can go on a piece of flat surface. On this direction, there is green grass. On that direction, there is fire. There is water here. So maybe your feet will get wet, or that's a less positive thing, as opposed to walking on grass can be more positive thing. Walking on fire will be dangerous thing, and walking on just plain soil is kind of neutral thing. So there's nothing to plain ground, and so there's nothing to accomplish right there. So that's how I should say this is plus and this is more of a single negative, feet getting wet. So that's how you have to understand as to what possible outcomes you might get, and you're not into maximizing the short-term reward, but a long-term walking around the park. That's the underlying idea. So now we'll see an application of the same concept in a slightly simpler example of a vacuum cleaner. Vacuum cleaner. So we have vacuum cleaning techniques, variety of these people, manufacturers like Roomba, is a very well-known company that is kind of, I don't like them. There are other companies that make a better product, like Xiaomi. It makes a wonderful vacuum cleaner, and there are other players. But let's go look at this idea of a vacuum cleaner. And so let's go understand our observations, our actions, and our result. The result is very clear. We want a clean room. The clean room doesn't happen magically. It has to actually do vacuuming. So the action to do vacuuming is that we are at this point and we want to go forward, or we go in this direction next, or we go in that direction next, or some other direction. So basically we have to understand what angle we go and what probability do we assign to that angular motion. So we could take a position that, I want to wake with certain probability P, I would travel at an angle R. That could be a decision I make. And so that's the one possible outcome. And so the idea is that you could move forward with a probability P. Every second I move with a probability P, and randomly rotate left or right with a probability of 1 minus P. So I go forward with the probability P, and I rotate an angle with a probability of 1 minus p. So I can go straight every second. I make a straight decision. Sometimes I make a go around decision. So I turn. So this is the probability p kicking in, probability p, probability p, probability p, and now probability 1 minus p. The other case, when the chance did not happen, then I don't go straight, but I turn. And then I move in that direction. And then I keep going. So p, p, like that, until the other case happens, in which case I turn again. And that's a stochastic way of moving around. And this motion is basically crazy. You walk like a crazy person around the room in the hopes that these kind of motions will eventually cover every single area. So you have the room and you're like walking like crazy. And you assume that this kind of a random walk will eventually cover the whole area and clean up the room. Well, that's a good course of action, but it's kind of not the best course of action, because the ideal course of action would be to clean up the room as quickly as you can and be done with cleaning and just move on. So that crazy random motion doesn't actually lead to a best excuse me. So this crazy random motion doesn't actually lead us to the best possible solution, because our best possible ideal vacuum cleaner should just start the vacuuming, find out what are the bad spots, clean them quickly, cover the whole room, and back in its place, back to the spot. That's the ultimate vacuum cleaner. But it's hard for a vacuum to just take a look at where the dirt is and then I just go target those dirty spots and I'm done. That's kind of not practically possible. So it has to cover the whole room, which is, I think, also gives us this subjective satisfaction of cleaning, so that the vacuum cleaner actually cleaned the whole room. And that's the ultimate idea, is to do it quickly and pick all the dust and finish off and attempt to maximize what? What do you want to maximize here in the goal, the result, and the reward? The reward maximization for a vacuum cleaner would be to look at the amount of dust collected per 30 minutes. How much can you collect? So you would maximize this. Maybe it's a really dirty room, so you can just grab and collect. How much can you collect? That's the way to maximize. So this can be a good goal to accomplish. And based on this maximization technique, you have to really take that decision as to which direction do you now go from here. So this is the room, and the room is dirty. You are here. I mean, the machine player, the vacuum robot, is here. It can go in any direction. So usually it goes with this direction with a probability p, or otherwise it will go to a different direction in the probability 1 minus p. That's the random, erratic, stochastic motion. This is the stochastic policy. Now, here the policy contains two variables. One is the value p. The other variable is the angle r. So two variables you have to really use and attempt to maximize the collection of dust in the room as quickly as it can and finish off the whole area in the entirety of the room here. Now, that's the ultimate optimization we are trying to accomplish with only two parameters here, P and R. However, we try to find the best value of P and best value of R. That becomes a question of trial and error. And we can try searching the brute force way, meaning we'll try all possible cases and just try to search the game or search the best policy. Like, what should the probability P for going straight? And what should the probability P for going at an angle? I should say 1 minus P to go at an angle R. And so what should the R angle be? And what should the probability value P be, so that 1 minus P will be the motion to go at an angle, and P will be the probability to go to at angle 0, meaning no angle. So keep going straight. those two values, we can do a search in the policy domain. In the domain of all possible combinations of policy that attempts to maximize the collection of dust in a given room, find the best values of P and R. That's the optimization. And we want to search the best numbers. So the one approach will be to brute force. And brute force, just try everything. Try this, try that, try this, try that, and find out eventually what works best. Now that is a gigantic, gigantic possibilities exist. Possibilities. Lots of possibilities exist in that space. So out of brute force, we try to find out what the right value of P and R. It will take forever to come up with that. So this technique of brute force is not the best, of course, because there are lots and lots and lots of possibilities of P's and R that you can actually take that will optimize. So you really find out the best to optimize the amount of dust gathered in a period of time. Then, it's basically searching the best possible policy to go move around in a room with the goal of maximizing dust collection. So brute force is not the best, bottom line. So we'll try another way, another technique. So the other technique will be how Darwin thinks. Darwin thinks that, you have genes, and you have a gene pool, and then you have offsprings, and effectively the Darwin concept is that if you have good genes, they survive, bad genes die. That's the way of thinking of Darwinism and genetics. So what we do is we attempt to use the genetic logic to find out what the best policy would be. So in the policy space, lots of policies. One approach, search the best, brute force, doesn't work. This approach, it's not the best. So we try the genetic approach. And the genetic approach, what we are really doing is find out certain things that you pick some 100 different types of sets of values of P's and R. Play with them. Only 100 as opposed to millions of possible values, or even more than millions. So you go with 100. You play with all of them. You find out which one perform better, which one don't, comparatively speaking, and you put a Pareto principle in there, 20-80. 80-20 rule you apply, and these are the ones that perform better. These suck. I should not use the word suck because we're talking about vacuum, and vacuums that suck are actually good. So sucking is not the right word. So bad. So bad policy. And so these actually suck. So they're good. And so bad. So you just kill them. Kill. And then when you kill, you use these 20 genes to create offsprings. And so you create 4 offsprings, 1, 2, 3, 4. And you add these guys, 20 plus 4, in your generation number 1. So first generation of policy. And you're using these 24 to basically create and identify the best possible iteration. So in the policy space, you have 4 points that you create based on the agent's behavior. The agent decides that, the agent is basically our machine pair. The machine decides to walk around like this, walk around like that, walk around like this, or like that. And so various combinations you see, and you notice that some of them will be again applied 80-20 rule one more time in the second generation. And you will eventually reach a point which is kind of okay in terms of the potential candidate to really accomplish the ultimate goal of cleaning up as much dust as you can in a given period of time, maximizing that. But then there are other techniques also. And that other technique involves simple math. And that third technique is what I would call gradient optimization. And what we're really doing is basically calculating the gradient or partial derivative of reward versus the parameters. Take a partial derivative like that. So you have the parameters are P and R, probability of moving forward, probability of 1 minus p of moving in the angle r. And so that's the two parameters we have at hand right now. And so we'll somehow come up with this mathematical partial derivative approach of reward. How does the reward change when I change r? How does the reward change when I change p, the probability? And thereby we are trying to estimate a gradient of maximizing the reward. And then we'll run our gradient ascent algorithm. So what we are really looking at is to maximize our reward here. And we are looking in the policy space. We are identifying policy gradients, which are basically policy parameters that you will tweak to maximize the reward, and you will apply gradient ascent algorithm to do a policy gradient based search of the best, or I would say the one that maximizes your reward based on this technique of ascent, gradient ascent, and you will find out that technique. And that will lead you to finding out the best parameters, P and R. And that way you will know what the right course of action would be for a given scenario to maximize the dust collection. So this concept is the idea underneath the technique that we are discussing in the first attempt, in the first part of the book, is basically policy gradients. That's what we began discussing here. Policy gradients, the very first thing. The second thing will be deep Q networks and Markov decision process, and so we'll get to that. That it's after the policy gradient discussion. Okay, so this idea of doing this kind of a math is in real life is kind of difficult, in that you actually have to have a dirty room with dirt, and all other circumstances should be mathematically constant, and you should be able to reproduce the exact same dirty room again and again and again. That's kind of difficult, right? You have some dirt and you want the vacuum to go around and clean, and you want to reproduce the same experiment over and over and over again, so that you really optimize. You want to optimize the way this thing moves, the way this thing moves and collects all the dirt. And so once you do it one time, you want to do it 100 times. You want to have the exact same dirt, which is kind of difficult. You can get approximately same dirt by doing it manually, and doing it manually becomes boring and time consuming. Excuse me. Becomes boring and time consuming and expensive. So what do? We simulate. We simulate real life. And that simulation happens in what is known as an AI gym. It's a gymnasium which lets us simulate real life conceptually, or rather I should say mathematically. And so this simulation has to be written. And by the way, there are people who have written it for us in a library called OpenAI Gym. And that is already written for us. That's what we are looking at here. It's a simulation of the real world. This is an environment where the robot can go and clean. And I can make the room dirty again and ask the robot to clean again and do it 100 times, 100 million times. It's all software. It's simulation. So the simulation happens in this OpenAI Gym. You basically install some Python package and you gym. That's how you get the gym running. So that's easy. Now, when you have the gym functional, you import the gym and you make a new gym. like right here. So you set an environment and say, you know what, Jim, make something. Hey, make me a card pole. So it will make you a card pole setup, which is not going to be like the dirty room setup, but it will be a card pole setup. And in that scenario, you will get a pole, you will get a line, a motion on this x-axis, negative x, positive x, and you will get this item to move around. You can go this direction, make it go this direction. The pole itself can fall at an angle with an angular velocity and angle. It has a position. It has its own velocity this way or that way. So these four metrics, let's call them 1, 2, 3, and 4. These four metrics are available to us already in the AI gym. When you say cart pole, it will create a new cart pole for you. In the environment will be constructed. And when you say, give me an observation, it will give you these four observations, 0, 1, 2, and 3, which basically means position, velocity, angle, angular velocity. These four values will be given to you in an array. Whenever you ask for observations, give me the observations. So observations right there. Position, velocity, angle, angular velocity. You get an array containing these values. That's the state of affairs in a given OpenAI gym for cart pole. So now you have a simulation ready for you, which is quite handy to say the least, because you don't actually have to have a physical object like this. By the way, you must have seen a video of this cart pole thing. Just pull it up. Well, I must have shown it to you a long while ago, I guess. But if not, let's go quickly watch it and so see what happens. And I'm going to zoom forward. I suspect I showed it to you, didn't I?
Yeah, we saw this one before.
Yeah, a long time ago. So the idea is clear now. You know, we get four values for any given position in an AI gym. This is completely simulated environment, so we don't have to have like this kind of a physical setup. It's nice to have this thing to play around with. And yes, you can apply the program in the notebook to such a physical object and have this pole balance itself after like 200 to 300 attempts. You will have the pole comfortably balanced right there. And not like this, but this is like tilted a little bit. It will be perfectly straight balanced because your technique, this machine, will learn how to balance it correctly. That happens through learning. And that's what you will see now in a simulated environment first, because I don't have that object with me. This object is actually nice to have. I'll probably get this object in my studio at some time. I'll find it out. Maybe I'll build it. This is, you know, some expensive stepper motor gear, apparently. Stepper motor gear equipment right there. And some interface to control it through a laptop. And just a pole and a platform to move around. So not much. But this is definitely a stepper motor. So that is, it has to be accurate in its motion and all the characters that we expect. It should match what we are trying to do in the simulation. It should match real life. So that's the idea. So let's go see here. So in our simulation, we get these observations at any given time. And what we really want to do in our simulation is that we want to balance the pole. And so we have to take action. The action in our example will be very, very simple. Either we go this way or we go that way. That's the only action. Like there's nothing much to do. And the result is actually, there are two parts to the result. The result is that one part is that the pole is balanced. And the second part of the result is the pole is within the screen or within the range of this. So it has a limitation on the range of motion. It can go from the left side to the, oops, I accidentally stopped sharing. Share again. So it will go from this point to this point. That's the limit. So it has to be within the range and also be steady, straight up like this. So that's the two goals. We have to be within the range, balanced and within range. That's what we want to optimize on. If it goes out of range, it is not really controllable because it will just fall this direction. Or if you go up to this point, it will fall this direction. And that's not what you want, because there's nothing to do in terms of balancing at that point or in this corner. So you cannot really balance it because you cannot move beyond this point. So it is going to go off balance and fall, or fall this direction. So either way, it has to be within the range and balanced. That's the results that we accomplish. And we take actions. They're very, very simple. Go left, go right. That's it. Nothing much. That's the cart pole setup in our OpenAI gym. So what we do is we next, set up some image rendering so we can see it visually. This visualization happens like this. And so you can see the visualization of this cart pole right in the notebook. So let's see if I can, I just want to close this notebook and halt and run it again and step by step execute up to the point where we are, which is where we should start seeing the actual activity done by this thing, the cart pole thing in OpenAI gym. That should show up right here. So I'm going to start executing, setup, import some basic functions to draw a figure, and introduction to OpenAI gym. We begin with a Pacman. So this is Pacman being loaded. And so we can load Pacman environment and we can reset it and we define its shape. So that observation shape, you can see that the observations here, oops, I'm clicking wrong button accidentally. Okay, there. You can see that the observations in a Pac-Man game are quite a bit, and not just 4 things in case of a cart pole. Lots of variations to that. And so we have observations vary depending on the environment. In this case, RGB image, 3D NumPy array, height, width channels, 3 channels. So we have 3 channels here. RGB color. In our case, in this setup, that's the result we are expecting to see. So I am going to execute that line to see shape of the array. And here is the shape. 210 by 160 by 3. That's a 3D array, NumPy array. And we can render it. And so the plot shows up like this. This is your Pac-Man. That's your visualization. Now let's see if we can proceed forward with this visualization to our cart pole discussion, which is, I think this is just a way of describing the OpenAI gym. So I'm just moving forward with this. There's nothing much to it. So create a little helper function to plot the environment. In this case, our actions that a Pac-Man a game player can do, there are 9 actions. The 9 actions are center, up, right, left, down, upper right, upper left, lower right, lower left. Basically, these are the keys that you can move. Upper right, upper left, lower right, lower left, and then 0. That's it. Center. Those are 9 actions you can take, and those are the action space output from the Pac-Man environment. And that's what you're looking at in this picture, the actions you can take. You can, of course, go forward. So I'll proceed forward. We are discussing cart pole, not Pac-Man. So clearing it, moving forward. And I think here they are showing you how the steps was taken, so it moved. And you can see the reward changes, shape doesn't change. The rewards did not change. They're still at 0 points. When the game is over, and then there is a done function. So if done is true, mean the game is over. So you're done. Done is not done, so it is still false. That's this example. And we can play one full game in 3 lives, moving random direction in 10 steps at a time. So now show the actual action of play, and we'll plot this, and we'll see a video right here. I hope video plays through. And so this video is expected to show you the machine playing Pac-Man as opposed to people playing Pac-Man. So you can see that it is a little bit of a motion that you can probably see. Yeah, so it's showing nicely. Yeah, so you saw some steps that the machine played, and it is accumulating certain points. And once it's done doing its thing, there are probably 10 steps that the machine moves around and eats these pebbles and tries to not die. and it is trying to optimize the motion that it is doing to basically avoid death. And I think it died. So that's Pac-Man dying. Then once we are done with this, we'll move forward. So I'm going to now close the environment. So now we'll go to the cart pole, which is what we wanted to discuss to begin with. So here is our cart pole. We are creating a cart pole gym. We are resetting the environment, getting our first set of observations. So here we are. We got a first set of observations that are your position, your velocity, your angle, your angular velocity. So 4 things, 1, 2, 3, 4. That's a 4 floating point numbers representing the 4 things that I just mentioned. Now we can render this visually. And so there are a couple of rendering issues that we need to have. So I think this is possibly taken care of in my setup, but this is something that you may have to do in your computer. If you get stuck with this, ping me and I'll fix it. I think it should just show it in my setup, meaning I don't probably not going to run into rendering issues. And so it will show the cart pole now. So we'll go forward executing these things, which is where we are fixing the issues. And then we see our observations. So here we go. That's our observation right there. Now the action space. This observation, as you can see, is the initial observation of the cart pole render, which is a set of basically small numbers, close to 0. Excuse me. Oh my God. So these numbers are close to 0, as you can notice right here. Pretty small numbers. That's why you see that the representation of cart pole as shown by these numbers is, by the way, they will change a little bit on machine to machine. So these numbers will be different based on how the OpenAI gym is set up and the underlying operating system. In my case, it's a Linux box. In your case, it may be different. Maybe you may be running it directly on a Mac or some cloud setup, who knows. So it will have slightly different values to the actual array observations. They may be different, of course. And so having seen that, the rendering shows up like this figure. And here are the XY positions of the mouse cursor pointer, but the pole itself is where it is right now. Now we'll see the action that you can take. So in the action space, there are not much actions except only two. And those two actions are go left, go right. Very simple. Cart left or right. That's it. Two actions. So what we want to do is push the cart left until the pole falls. We're going to push it this way, and we expect the pole to fall like this. And that's what we are going to do, is we reset our environment, and while true, it's an infinite loop. And we are going to observation, rewards, done, and info, the 4 parameters that we are handling. And when it is done, we break. So that's a continuous loop that we going or keep on running. And when it falls off when the cart pole falls, the game is over. And that's where done is true. And so that means the game is over. That means you stop playing. So that's the done break scenario. We will sometimes plots in the previous cell so that you plot close and then render the cart pole one more time. So I'm going to erase this ink and execute these steps. And we will now go to plot it. So the plotting is here. And we now see the image shape. Here. The game is over and the pole tilts too much, not when it actually falls. Now let's reset the environment and push the cart to the right instead. So we are now pushing the cart to the right. In the previous example, we pushed the cart, this cart. But 0 means you're pushing it to the left side, and 1 means you're pushing it to the right side. That's the step function here. So the step in the previous condition was, erase. And here, our previous step involved a left motion until it dies, right there. So this is your left motion, step taking towards left until the pole falls, until done equals true. So when it is done, it falls, and then that's what you see. You see more, make it go like that. The pole is going to go this direction a little bit, and that's when it is considered as done, meaning that's when it breaks. The other extreme of the other push, the right push, you will see that you are now going to go through the other direction of push with a flag of environment step 1, and so the pole goes the other direction here. So your step 1 is meaning you push it this way. And as a consequence, the item is going to fall this direction, and that's when it breaks. And so you see that this cart pole environment is showing you the right motion, the right direction push. And so it is doing what it is doing. By the way, this game is over when the pole tilts too much, not when it actually falls. That's how you don't see the pole falling all the way down like this. You don't see it that way, or the other direction, which is the other example. In the other earlier example, that course, the pole can fall this way all the way, but that's not the point. It is considered break, or rather done equals true when the pole tilts too much, that it is beyond repair. It will now fall no matter what you do. And so at a certain angle, it is considered to be more than tilted enough to fall no matter what you do, whether you push this way or that way, it will still fall. And so when it tilts beyond a certain angle, it is considered game over. That's why you don't actually see the pole tilted all the way flat like this, or maybe even down like this, dangling down like this. And that's the idea behind the definition in this environment. This AI gym happens to be that when it tilts a little bit too much, then it is beyond repairable. In that case, game over, because you cannot fix it. Okay, let's go forward. Now we will apply a simple policy to manage our pole and try to keep it up in the air. And this is the policy implementation right here. But we will go back to the book and read about it and discuss about it before we come here. So we'll now go back to where we were in the book as we discuss these things here. And so the idea underlying here is that we want to actually put a policy in place. So I think we discussed this already on the notebook. So the game over, episode is over when the pole tilts too much. It doesn't have to have a fall like all the way. It is just considered over, done equals true. Game over. When it tilts too much. And so that's the idea behind done. Done equals true. Now we'll set a simple policy. This policy is actually logical and simple to understand. So you will see what we are really trying to accomplish is that we will push. It's very, very logical. So let's go draw it. We have the pole, and if it attempts to fall this direction, then we will push this direction. Simple. That's naturally instinctive way of making sure that the pole is straight or vertical. So the other logic is that if you see that the pole is falling a little bit that direction, this way, that you push this way. That's the policy. I mean, there's nothing much to it. That's how naturally people balance. And people are way, way smarter than machines. And so the machine may not be able to simply balance just by this trivial, simple policy. But that is what instinctively people do, is they take a cart pole and try to balance on their hand. They will do it exactly like that. If a pole falls this direction, you pull it that direction. And if the pole falls that direction, you push it that direction. So that's the idea. That's the simple policy we are going to discuss right here and implement. Give me a second. So how do you implement that policy? Let's go see that. We define a policy as a function. And in that function, what we're really doing is looking at our parameters of position, velocity, angle, angular velocity. These are the 4 observations that you receive: 0, 1, 2, 3. And what we're really trying to do in case of a basic policy implementation is that this angle is what we are really after, this angle. If you see that the angle is this direction versus that direction, that's what we really want to take an observation and pay attention to as an input into the system. Looking at an observation, and we find that the angle in the array look at this metric, and based on that, we will go plus or minus, or I should say 0 or 1, or I should say left or right, or whatever you call. That's the action taken. And simply speaking, if the angle is positive, I should redraw these things. If the angle is positive, meaning it is this direction, it's positive, let's call it that. And so you need to move the thing right direction. If the angle is negative, that means this value is negative in the array, in the observation array. Did you take the action left to take a corrective action? And that's what we are really trying to draw in our basic policy function definition. We are feeding in observations, which are these, and setting out this angle observation from the array, this item. Look at that angle, and if the angle is less than 0, then you return 0. If the angle is more than 0 or equal to 0, you return 1. So that's the idea here. If angle is more than 0, you return 1. If the angle is less than 0, you return 0. That's the action to be taken. That's your action function. That's what we are returning. And that's our policy implemented right here in these 3 lines. These 3 lines define our policy. So it's simple to understand that way, right there. So policy defined. Now we are going to use it. How do we use it? Right here. What are we really doing is beginning with an empty array, totals. We are going to run multiple episodes. We begin with a reward of 0. We reset our environment. And then we start iterating on a for loop. And we put an artificial limit here, 1000. This 1000 basically is that you don't run forever. Otherwise, you will keep calculating forever. And so you don't want to run forever. You just break at that point, 1000 steps. And you take an action based on what you observe in the policy. If you observe that the angle is this way, then you take this action. Angle is this way, you take this action. That's your policy implemented right here. And so based on that action, things will happen. In the OpenAI gym, in the simulation, you take an action. This produces next set of results in the observation set. And so you take another action. It will generate another observation. You take one more action. It will generate one more observation. What is trying to simulate is real life. So you take an action. The cart pole, which seems to be falling this direction, gets adjusted a little bit like that. And so now you get a new angle. This was the first angle. This is the new angle. And so you get new observations every time you take an action. So you take an action. I should say action. You get a new angle. It was this angle before, so you go this direction, and now you get the other angle. So you take the next action will be this force. So the other left force. You basically set 0 action. This action was action 1. One action is to go right direction. And the next action will be 0, meaning you go left direction. And so you will see that the pole will bounce back into the other angle. And you will eventually learn is the underlying hypothesis in this algorithm, is that the idea is to somehow learn to balance and set a policy like this to evaluate. You take an action and you get a reward as a consequence, and you accumulate your rewards pretty much like that. And when you're done, in the game over, you break it. Game is over. And at the end, you will maximize your rewards. And then you add it to the totals. So you will basically accumulate. And the results, as you can see, mean, standard deviation, minimum, and maximum are the total results that you get from the episode of 500 episodes. And that's the result you get, mean, standard deviation. And so what we are looking at is the 68 number here. We tried 500 times, and the maximum we could sustain was 68 consecutive steps. The best case scenario, max 68, max totals. Essentially, in 500 attempts, we were able to manage it only 68 number of times, 68 number of consecutive steps. So if you have step number 1, step number 2, step number 3, 4, 5, somehow we have to balance it. Out of 68 steps, 69 step, it falls. And so you tried 500 times, by the way. And this is the best case scenario. It's a pretty lame result. You know, it is like me trying to balance a card pull for real. I cannot balance. And so this is pretty much me. There are people who do that comfortably, no problem. Just balance the pole in their hand, and they're able to accomplish. Just hold it forever, perpetually. I suck, and so when I hold the pole in my hand, it will fall within like 3 or 4 motions. It will probably fall, but that's just me. So this is a sucky algorithm, sucks, and it's not a vacuum cleaner, so it actually sucks. And so 68, bad maximum. I mean, I'm not impressed. I don't think anybody is. And so this needs to be improved. So we will apply a neural network right now to this technique. By the way, I should run it. So let's go clear the drawings and go to the browser window and run the thing. And so hard-coded policy based on what we just discussed. Same idea that we just saw in the book, implemented here. And we just, boom, run it. And we will now see the video. Hope it shows. There we go. And I think it broke in 3 attempts, 3 or 4 attempts. I don't know how many attempts was that, but the game is over. And so we'll try to run one more time. We'll go back to the policy, execute, and show the video. It died in three runs, apparently. So it's pretty bad. One last time, execute, play the video. 4 attempts and dies. So pretty lame. Yeah. Just a few wobbles. System is unstable. After just a few wobbles, the pole ends up tilted too much and game is over. You need to be smarter than that. So you will apply neural network techniques. Let's see what that turns out to be, or how it looks like to be. In our case, the neural network is actually something that we are very familiar with in the past examples. We can apply the same in this context. And we'll just see what it means to us in a cart pole example as to what neural network might be a good one. And we know that there are 4 inputs. There is only one action. And so that makes it a whole lot simple. So what we will do is we will come up with some kind of an output that produces a probability P by which we'll go to this direction. And of course, that means the probability 1 minus P that we go in this direction. So this is the action. And so this probability can be in the example 0.3. So in this example, it will be 0.7. So with some probability as an outcome based on what we see as an input there are 4 items: position, velocity, angle, angular velocity. 4 inputs, 1 output, basically the probability P. That's the output. And when you're talking about probability, you want to actually produce an output that looks like something between 0 and 1. And so you would go pick our classic sigmoid function that generates a value between 0 and 1, pretty much like that. So it's your sigmoid. That's what you want as an output, because you want to generate the value p. And based on this number p, if p is 0, you would definitely go that direction. Action 1. If p is 1, you definitely go this direction. Action 0. And p somewhere in between 0 and 1, like a sigmoid would, you will have certain probability of moving this direction or that direction based on the probabilistic nature of this output. And this is your input. So the creation of a neural network becomes very, very simple. It will look something like this. So what we have our observations as input, and we will put in a hidden layer, and then we just put in a sigmoid function after that calculates the probability of action 0, p, or left action. The hidden layer here, 4 items. They are your ReLU functions, filtered out with ReLU, and you're basically setting neurons, input neurons, 1 hidden layer, 1 output layer, and you have some multinomial sampling. So this is random sampling based on the probabilistic nature of the motion that you will take. So based on these probabilities of 0.3 and 0.7, this multinomial sampling will make a decision whether you play a 0 or a 1 based on the probability of p. The value p, the value 1 minus p, you will take this action. That's what this multinomial sampling does. Is basically it produces an action that feeds the probability into the system and generates 0 or 1 with a chance of p of 1 minus p. That's multinomial sampling output. Basically, the same p applied to an action, nothing much to that. So the question that you will probably think of is, why are we even assigning these probabilities to the output? Why not just come up with a straight 0 or 1 and just be done with it? Why have this chance like that, or some other number like that? Why even have these kind of chances? So the way to think about this is that if you go to a restaurant, and it's a good restaurant, there are 100 items in the menu, and you come in, you look at the menu, they all look awesome in the menu. So the chance of you picking any one of these 100 items is kind of equal. It's basically a 1 in 100 chance that you will pick any one item, because you are basically equally likely to pick any item that you want to eat, because all of them look good. It's a good restaurant. So you go and order one. Let's say you order this item number 93, randomly selected. So you eat that and you like it. Next time you come again, the same restaurant, same menu items, but you know that you have tried 93 before and it was good. So now you want to assign, make a decision again. So what do I eat today? Eat what? What do I eat today? So you can then say that, you know what, I liked 93, so I'm going to repeat that, and I will keep repeating that because it was awesome. And so thereby you can potentially run into a scenario where you are assigning 100% chance of this being selected because you liked it in the past, and you are ignoring all these items. 0% chance. But if you go that route, you will never even venture or figure out what these things taste like. That is why you don't want to assign 100% probability of selection to that particular item you have tried in the past, because you want to explore what else is on the menu, as opposed to what you know works well. This is the exploit scenario. You know this one was good, so you exploit it, and you repeatedly eat the same thing over and over again. You may be happy, but you're missing out on what else may be there, and that's the chance of exploration. So that's the underlying idea, is that you don't want to assign these 100 items with a probability maybe a little bit more of, like, the item number 93. Maybe you give it a 10 out of 100 chance. 100 chance. You're likely to take that because you know it is good, but you have heard other items on the menu are also good. So you give these other guys, say about 90 out of 100 chance on the 99 items. So divide by 99. That's the probability you will assign to all other items. But this one gets a 10% chance. And everybody else gets a uniformly distributed 90% divided by 99 chance of being selected as your item that you will eat. And thereby you're reducing the probability of this known good item you want to exploit, because you not just want to exploit, but you also want to explore. And that's the scenario we are dealing with here, is we have an output that says, you know what, you can take this action or you can take this action, but very likely you should take this action, and maybe you want to give it this low probability for the other action. And so that's the underlying idea behind assigning a probability to a move or an action for an event that comes in as an input. For a cart pole falling that direction, you want to move it this way, 90% of the chance, but maybe you want to go that way, 10% of the chance. So that's the idea underlying behind the concept of multinomial sampling, as to why you want to assign probabilistic actions, or rather, why do you want to apply probability to an action, so that you explore what else might actually cause the cart pole to stand correctly vertically. It's an exploratory nature of this probability that might lead to an eventual correct standing balancing cart pole. That's the underlying logic behind using a probabilistic distribution like our sigmoid function. So you will get some value in between, which is going to be the output of this sigmoid. So now let's implement this network to see how this will be used and trained and applied, and see what the result turns out to be. So that's the underlying concept. What we are really accomplishing is we want to maximize our goal, which is to balance the pole and not fall off, sustain the game for a long time, ideally perpetually. And yeah, basically that's the goal. Yeah, win. The goal is to win. And so balance the pole. So we'll now see how we can implement this. Another thing to think about in this is that, any action at a given time in a cart pole setup really depends on what is the current state. Like, what do we observe? We observe those four things, position, velocity, angle, angular velocity. Those are four things we observe. And any future action strictly depends on this observation. It has no bearing on any past observations. Like in our LSTM discussion, it tries to keep in mind what happened in the past. In our example of a card poll, there is no need for a memory. You can ignore the history. Past can be comfortably ignored because there is no such need for the action that you take doesn't actually depend on what was the case in the past. So you can comfortably ignore the past. It's not relevant, actually speaking. So in that case, you don't have to apply these time-based techniques or memory-based techniques in our example. That's one idea that I think I need to point out, because it doesn't involve history. It doesn't need to have memory. All it needs to do is to just get these 4 values. Sometimes you need to apply a little bit of different setup in the problem of running a neural network, in that if the observations themselves have noise, they have incorrect observations itself. So that, we are in our assumptions, we are taking the simplistic assumption that the observations are not noisy. There is no noise. So we can just go with the idea that we just discussed here in our implementation of the neural network like that. That's the reason why we are choosing those methods. Simple. This is a simpler example, by the way. And so we will now apply this concept using TensorFlow. We'll specify what inputs we have. How many inputs we have? 4. How many hidden neurons do we need to have? Again, 4. We don't need more. It's a simple task. So it's a simpler example. So 4 neurons in the hidden layer and only 1 output neuron that outputs the probability of accelerating this direction, the 0 action, the probability P corresponding to that. That's what we're really trying to evaluate as an output, because we know the other action is action 1, and the probability of that will be the other probability value, the corresponding complementary probability, which is 1 minus P. And so that is implied. We don't need to calculate that as an output, or don't need to predict that or estimate that as an output, because it is mathematically derived. All we really need to do is come up with this number P, because that one is a mathematical output. 1 minus P, action 1, P, action 0. So it's simple that way. This is the output we want. And so we have just one output. And so that's the 3 numbers set. And then we initialize. And variance scaling initializer. That's an initializer that we are choosing in setting up the beginning point. Now we set a placeholder variable X for our inputs that are going to come. Those are 4 values: position, velocity, angle, angular velocity. Those 4 values will come, and the 4 numbers here, and input. Then we have hidden layers. We are setting up ELU optimization and kernel initializer. In our logits, which is the last step that calculates this probability, the output layer, we are setting up n outputs as only 1. So this is the value 1 here. And we are creating an output layer for the logits. So this is the output layer for the logits. Then we apply a sigmoid to that. That produces the actual output. So there has to be a sigmoid function that implements this math on the output. So that sigmoid is applied right here. And then we have a random action. That random action is basically based on our P output. So this P, this is your output. And so the other is 1 minus output. That's the other action you can take potentially. And that's what you're looking at here in this scenario, outputs and 1 minus outputs. You're creating an array, a concatenation of these 2 values. This one, and sorry, P and 1 minus P, these 2. That's what you're really trying to concatenate and create a p left and right as a new variable. And you're using that p left and right as a variable to come up with a multinomial action. Multinomial action basically stands for the input that you pass, which is p. Also implied is the value of 1 minus p in there, mathematically derived. You create an array like that. Here, this is called your p left and right. This is your left probability, this is your right probability. And based on these inputs, you want to come up with a number which is either a 0 or a 1. So the idea behind multinomial is to generate a 0 with the probability of p and generate a 1 with the probability of 1 minus p. So it basically outputs a 0 or a 1. That's the action you want to produce. And then you initialize global variables and execute. So the execution happens when you initialize a session. That's the next action you will see down in the book. So I'll scroll now. We'll also go to the our what is called Python notebook. That will help us running this. And we would like to train it also. So that's the idea. So we'll go to that and understand how do we set a neural network, and then okay, I'm going to execute these steps. So neural network policies, P and 1 minus P, fully connected network, 4 hidden layers, 4 input layers, and 1 output layer. It is giving us a deprecation warning, which is fine for now. And then we'll randomly initialize the policy and then use it to play one game, 1,000 steps, initialize the session, and see how it actually plays out. So I'm going to assign, execute the initialization, and then establish and run a session. So it ran. Now we'll see how the video shows. It is also bad. Yeah, this was bad. You have to train the network. That's what we haven't done yet. So we just ran. But we have to understand what can we do to make sure that we optimize and train the network properly. So that's where this other action comes along. So the concept of training a network involves mathematically optimizing something, essentially. And so we want to optimize it, and we want to assign what I call, I think this deserved a discussion. So the idea is that you want to, you have a dog, and the dog needs training. So you give it a treat. And when the dog does sit, and the dog actually sits down like this, dog sitting. And so in that case, the dog sat, so you treat. And that way, the dog is getting trained. Over time, it will know that when you say sit, that the dog is supposed to sit down. And when the dog sits, that you get a treat. And you repeat this over and over and over and over again, and the dog will learn. Sit, sit down. Got it. Dog understands sit. Sweet. Now, make it complex. You have the dog. Dog gets up in the morning, and dog goes out in the backyard on his own, opens the door, does his morning business, comes back inside, cleans his feet before the dog walks on the carpet, and then behaves all nice during the day, and in the night, goes to bed on its own without howling, without making any noise. That's a good dog. And at the end of the day, you give the dog a treat for good behavior during the day. Excuse me. So this dog is actually, maybe a good dog. I mean, it's awesome to have such a dog like that who's, obedient, nice, and, well behaved and all that good stuff. But it is so hard to train the dog for such a behavior, because it is really difficult for this poor dog to understand why are you giving him a treat, for which specific action that he does. In the morning action, cleaning the feet action, behave all nice action, goes to bed on time action, which action is being rewarded. Dog has no clue. No clue. That's the problem. So we have to find out that you want to credit the dog with a treat. So credit the dog, give it a treat T to the dog D, and say, I'll give you a credit if you sit when I say sit, that you sit. And if you do this, if I say this, you sit down, I give you a treat. That's a very direct action. You're assigning a credit of the treat to the dog. Awesome. That's the credit assignment problem that we are really dealing with in case of a real life situation, when the action you take does not result in a reward immediately. You don't get the treat right away. You get the treat at the end of the day, like here, for good behavior throughout the day. Oh, that's hard, because I don't know where or which action are you really rewarding my behavior. Where am I assigning the credit? So there comes the problem of assigning a credit to an action. That, what, you have the cart pole and you move it this direction, so you took that action, so as a consequence I should maybe give you a treat. And then you get another input, and then you move the cart pole this direction, so you did a good job, I should give you a treat. So these tiny treats you cannot really accumulate like that, because the idea is so hard to understand and so hard to actually estimate as to when should you assign a credit of a treat to an action that you take, because the ultimate result or a reward is not immediate. It is there, it is not immediate. Yeah, something like that. So no, it's not immediate. That reward of this sticking vertical in the range and not falling down is the reward. It is not, it's eventual. It's not immediate as a consequence of an action like this or an action like that. It is eventual reward that you get at the end of the day. The dog behaves properly, that you get a reward. But that leads to the credit assignment problem. So how do you then solve this problem, and how do you assign the credit for an action that actually is the right treat, or right amount of treat, or right encouragement, or the right feedback that you want to give to an action, so that it knows that, what, my action was actually good in the long run. Even though it might feel like the wrong course of action right now, it may actually be a good one. And I'll give an example. If you have a cart pole with a limited range, and the cart is, falling this way. And so the natural instinct is to go, maybe I draw it a little bit too much. So maybe I'll go almost on the edge. I'm almost on the edge right here. And the cart pole is almost falling a little bit like that. It's falling this way, tiny little bit. At that point, does it make sense to push this way? Probably not. There's not much room. And you don't have much options either. So it is probably a case you can make that instead of pushing it this direction, I will push it this direction in the hopes, tiny little bit, tiny, not this much, tiny, in the hopes that it might balance. Because then I get some room. And then the next attempt, I will actually take a corrective action. So maybe this is the right action to take, even though pole seems to be falling in that direction. You can quickly move it this way and then attempt to balance it, because I then get some room, because I will be moving in that point, in that direction. I make some room right here. So in the next step, I can potentially balance my cart pole. So what you're really looking at is the reward is actually an accumulation of something that I do now, or something that will happen in the future step, and that something will happen in the future step, and that something will happen in the future step. And eventually, all these little pieces of reward needs to be accumulated in some fashion, because that's what counts. The reward that I take, the action that I take now, and the action that I take next, and the action taken next, and next, and next, and next, perpetually. All these rewards need to be aggregated. Now you can, of course, aggregate up to infinity, and that's not the right way to go, because you cannot mathematically calculate that. So the way to do this is the idea of time value of money. Time value of money. In other words, if I pay you $1 right now, versus I pay you $1 1 year from now, which one would you rather take? Would you take $1? I'm going to give it to you, right? Okay, take my dollar. And here, take $1 from me 1 year from now. Which one would you rather select? This or that? What do you think? So the way to think about time value of money is that value of money decays over time. I would rather get the money now, because the money that I have now, I can potentially invest it and make it grow a little bit. Similarly, if the money that I don't have now, the value of that is actually less to me right now, because I don't have it in my hand. If I had it, I would have invested and I would have got 2 extra cents. But the value of $1 1 year from now is a little bit less than the value that I have right now. And that's how I would tend to compare. So whatever we are looking at is this discounting is what is happening here. I'm discounting future values. Future values, whatever I'm getting, I'm discounting them a little bit, tiny little bit. And so what I want to be able to do is, in my calculation of rewards in the future, I will put in a discount factor. And I will square it with the order n. And I'll describe that a little bit better. So what I have is a reward right now. And then I get a reward in the next run. So I'll have a discount factor. And in the next run, then I have the next reward and discount factor again. In the next subsequent run, and a discount factor again, and another reward, and like that. And this number that I'm looking at is basically my 98%, the one that I just used for discounting money. You can adjust this number to 95, any number you like actually, or even better, 99. So you can play with this number to adjust the discount factor and come up with a mathematical way to calculate the accumulated reward. And that's the assignment you want to be able to do, because the guidance you want to provide to the machine playing the game or the agent, that guidance it gets is through this signal. This is the treat to the dog given at the end of the day for good behavior throughout the day. And so that's what we are really trying to assign appropriate credit for good behavior. Now here, these values can be negative or positive or negative or positive. And the overall action accumulated will be a different number and will be discounted into the future. So output that happens after like 5 steps is not as relevant. In fact, the output that happens after 13 steps, if you use this discount rate, for example, and you run it 13 times, it gives to about roughly 0.5. That means the output at the end of 13th step is half that relevant as the action or the result that I accomplish right now. So I run the game 13 steps, and then I get some reward, and I get reward here. This is half useful compared to this. So that is how you discount and aggregate the steps to collect and come up with an aggregate cumulative credit assignment to an action that you want to give to a machine or to an agent that is playing the game in your example. And so that's the concept of a discount rate. Typically, this is what I just used in our example. So 13 steps makes it a half. So it's discounted by half. $1 to me 13 years from now is like 50 cents. That's the idea. We are talking about time value of money versus this discount is a little bit conceptually similar, although it's not 13 years, but 13 steps. So now we go forward and understand how do we apply this idea of a action that you want to take and apply that to a given scenario. So we have the machine player, and that machine player is playing this action or that action, 1 or a 0, and you want to reward. So what we are doing is rewarding right here. We say, you know what, make a right movement. So if you make a right movement, you get a +10 reward. And you make another right movement, you get no reward. And you get another right movement, you get a -50 reward. Now what we are really doing in case of accumulation of the rewards in a discounted fashion is we are adding a discount ratio like that, like I just mentioned. And we are applying the ratio of 0.8 in this example, 0.8. And we are discounting that, bringing it now, and then doing it one more time, bringing it here, and then aggregating it. So this is the sum of discounted rewards. We are basically coming back from the future and trying to see what does that discounted reward really try to accumulate in terms of a reward given to an action that the reward actually happens sometime in the future or accumulated steps along the future. And we are really, comparatively speaking, talking about treating a dog at the end of a good behavior day throughout the day. So it's hard for the dog to understand why are you treating, which good behavior was treated. It has no clue. And so that's the idea. We are trying to understand how do we simulate that setup by introducing the concept of a discount rate. So now that we have a good understanding of how we can come up with an estimate for a given action, we'll now apply the training of policy gradients to our algorithm. So let's see how that actually plays out. So we have to, give me a second. So the technique that we are going to use is called a reinforcement technique or reinforce algorithm. That's one class of policy gradient algorithms. What we are really trying to accomplish is, in our policy space, identify the right policy to take an action by looking at the gradients of reward versus the action we can take. And that's the policy gradient. These are policy parameters, policy params. That's why we are calling it policy gradients. And so that's the concept we will see here. We have to keep running this on several episodes in order for us to then understand how does the actual action score based on this technique that I just mentioned here. This technique. So R, this technique of discounting to come up with a treat. And then, of course, at the end, it is simple to just run gradient descent. And so we'll implement this in this example using TensorFlow. The implementation begins with, first of all, taking the action, converting into a float, and 1 minus the action is the y value assigned. And this y value is basically probability must be 1 if the chosen action is this one probability, and probability is 0 if the chosen action is that one action, and this is your 0 action. This is your probability. So that's the value that we are basically calculating based on this simple math, y equals 1 minus action. It's action 0, action 1, probability 1, probability 1, probability 0. That's the simple formula implemented here. Then we define a learning rate. We pass it through sigmoid cross entropy function. We set the optimizer, and then we are trying to not actually optimize. And this is the difference here. In most other examples, we just run the optimizer to optimize and find the value, the minimum or maximum, whatever value we want to find out. But what we want to actually do is not find the actual optimal value, but instead compute gradients. So we are going to compute gradients and compute gradients. And that gradients is what we are trying to then assign the discounting like that to various steps gradients in the future. And then we accumulate all of them and then find out the optimization. The optimization will run, but not right now. So at this step, we are simply computing the gradients, not running the minimize method. So typically in past examples, we'll just try to optimize right there, try to minimize the entropy. In this example, we are not doing that yet. We're just estimating our gradients and then apply our discounts like that at various steps, and then optimize. So that's what you will see here. We have an interim placeholder to store the interim values, and I think this is best discussed in the book. So the notebook will have a much clear implementation written down. So I think I should just switch to the notebook. So in the notebook, we have seen this bad implementation of neural network. So we saw that. And what we need to now do is assign target probabilities and the training operations. So that's what we are going to run next, is reset the graph and set our, this is the minimize function. And I think in the next example, in the notebook, we should have the gradient calculations also. This is the minimization step, I think. So let me just go forward a little bit and read. Yeah, I think in the next example here is where you will have our gradients computed. So you compute gradients and then you apply the math that we just discussed about. And then you discount based on, so this is the next example. This one we'll go prior to that, prior to this discounting the discount rate, we'll have to run it without that. And that's the previous step. You don't have to run it, it's just an illustration here. That's before the policy gradients application. And so here, what we are doing is just running it and seeing what the iterations are for cart poll. 10 environments, 1,000 iterations each, and plot the view. It is also bad. It did not impress, but now let's see if it actually gets impressive. So policy gradients idea. So the idea here is to, first of all, let's go read this line by line. I think that's better. So we have to define target probability. This target probability is what we are really calculating here. If an action is good, we should increase its probability. And if it is bad, we should reduce that probability of action. So the action is y. Y is 1 minus action, essentially, effectively. The action that you take, convert into a float. And that's the underlying concept in the estimation of y. Let's go read further. So how do we know whether an action is good or bad? And that is, most of the actions have a delayed effect. Like, we don't know whether we'll get a treat at the end of the day because the dog behaved nicely throughout the day. He might get a treat. So when you win or lose, it's not clear immediately when you're playing or what actions will eventually lead us to a win or a higher score. That's not clear. And so it just depends on not just on the immediate action, but also any subsequent actions you will take. And so if you get a combined result, that's what you want to aggregate. So, you have to basically identify what action gets the credit. Is it the last 10 or last 60 steps? That's the credit assignment problem that I just discussed just a bit ago. And so what we're now going to do in our example here is assign this credit assignment problem incorporating our discounting rate that we just discussed early on. And the policy gradient algorithm will first play multiple games, then making the actions in good games slightly more likely, while actions in the bad games slightly less likely. So we have to adjust our actions based on multiple plays, and then we go back and think as to what we did. That's the idea. So here, TensorFlow, reset the graph, 4 inputs, 4 hidden, one output layer, learning rate, initializer, set a next placeholder, hidden layer. We are, creating a hidden layer in TensorFlow, creating a logic layer, creating an output layer based on sigmoid function, calculating P left and right based on the values of probability and 1 minus probability. And that array, that is what we are really estimating here. Then we are taking an action based on multinomial output of the log value of this. and giving it only one sample. So it is going to produce either a 0 or a 1 based on this probability or that probability. That's the output you will get in the action. And based on that action, we will have a Y value estimated. We calculate cross entropy based on sigmoid cross entropy with logits using the label Y. And logits, we assign Adam optimizer using the learning rate we have set here. We have gradients and variables that are going to compute the gradients, not actually attempting to minimize or maximize or optimize, just calculating the gradients right now. Then storing them here, setting placeholders for gradients and setting placeholder for gradients and variable feed, and then running an iteration loop on gradients and variables. Gradient placeholder is defined, gradient placeholder appended, and gradients and variables appended again. And so this is basically creating across multiple variables that you have accumulated, setting those placeholders, apply your gradients, which are basically run the optimizer at that point, and you are ready to initialize and save. So the next step will eventually run TensorFlow. This is just the setup of the problem. And we are also defining two functions. Those two functions are discounting. So we will see where the discounting comes into play. And so the idea of a discount, like we just discussed, is the discount rewards function, which takes a discounted rate and it fills up with zeros to begin with. Cumulative rewards are 0. Then it starts a for loop in the length of rewards, and cumulative rewards are your reward step, cumulative rewards times discounted rate. So this is basically going to add R or some reward that you get, plus the reward that you get again, plus the reward that you get again, like that. We keep on adding like that. And fill this up through the length of rewards. And that's the length that we are passing here for whatever number of rewards we are going to iterate on. And then it will store the discounted rewards in every step based on the interim values that you will accumulate, and return the discounted rewards. You want to then normalize these rewards. Normalization is basically minus mean divided by standard deviation for any value. And that's the normalization function. You will see that happen here. So minus mean divided by standard deviation is what you're returning. So you calculate mean, you calculate standard deviation, and then you return this. This is the normalized discounted reward. So you want to normalize this because it standardizes the output based on this concept of normalization. Value minus mean divided by sigma. And so defining these two functions helps us get the discount rewards at a discount rate of 80%, and you get this output. We will have to run this. And so here is your output of normalized rewards. So these are normalized numbers of the same output. Then we are going to create a gym, cart pole gym. How many games we play per update? So 10 games, 1, 2, 3, 4, like that, 10 games. And we'll accumulate rewards in that step, in the 10 steps, and then assign. In each step, we'll, each game that we play, 10 games, we'll have a limit of 1,000 iterations, 1,000 steps. Number of iterations, save iterations every 10 step, which is matching this. We are setting a discount rate of 0.95. And so these are example calculations. They don't actually use this rate. This is the rate that is going to be used. These are just sample calculations of these functions, this and that. So this is the calculation example, and this is the calculation example of these functions. Now here we are actually executing in a gym, assigning these values, and then setting up a session, initializing the run, iterating in the range, 250 iterations, and let's see how it plays out. So clearing my ink and beginning to execute this sequence. So on the top, policy gradients, execute 1, 2, 3, and this is the discount reward function defined. We'll just put some nominal values and estimate, see how it actually calculates that. And now we initialize our TensorFlow iterations. So here we go. And so it is running those iterations, 1, 2, 3, 4, 12, 15, whatever that number is. And soon it will finish 250 iterations. And then we close our environment and we'll see the animation after this 250 iterations finish in maybe about a minute. It should finish quickly. Is it slowing or what? I'm just anxious, so I'm going to go look at. Okay, it should finish. It is doing it. Yeah, 250 means it will take about a minute more roughly. So we are halfway through, close to that. It is getting slower and slower a little bit. Uh, 100 more to go. $184. Okay, do it quickly, man. I need to get a bigger machine. I guess more CPU. Or maybe a GPU. Yeah, my GPU on that machine is really cheap. It's a good CPU, but bad GPU. There's no display connected. So I should maybe grab a display card and add it. So 219 is finishing up quickly. Oh, I dislike waiting. But we are almost there. At least it's a counter that tells you that we are there. 249 coming up. There we go. Okay, that did it. So we are at the end of the iteration. We will now close our environment. And then, oops, did I run it again accidentally? Oh man, close it. And render, see what shows up. I bet nothing will show up because I was stupid. I accidentally closed on that button as opposed to this. So it will not show you until this run finishes, which is unfortunate, but While it does, we will go forward and discuss the next idea.
I
So-
can run it on my own.
Are you?
I can run it on my own.
Okay, fine. So I will proceed forward. So this is what we are going to see. Eventually, we'll see that. And now we will, by the way, the thing that you will see when it runs and actually is able to balance quite a bit decently. Excuse me. And the balancing happens decently. And by the way, this is the kind of concept that was used by AlphaGo. Pretty similar concept, except on a much complex problem of playing the game of Go. And they had a similar PG algorithm. This is policy gradient algorithm, and they added extra items in here, which is not described in the book beyond the scope. But there are other variations to this idea, which is what we will now discuss, is the concept of the second part of this chapter, which is your deep Q networks. That's what we want to get to our understanding as to what the policy gradient was. And we ran one example, and you saw that. You will eventually see that. We are beginning towards this concept, but it requires us to understand what is called Markov chain and Markov decision process, Markov DP. So that those two concepts we need to understand. So we have to first discuss that before we get to this idea. That's the last idea in the book, by the way. And this is what is used to play Pac-Man, that you can have the machine play Pac-Man. There is a code implemented in the notebook that plays Pac-Man, and you will see that it plays Pac-Man comfortably after like a couple of weeks of training. So you will have the program run for a few weeks, and then it will eventually finish. And so like it's about to finish, and we should be able to see the iteration pretty much soon. So that's what it will take you a couple of weeks to run on a laptop. You have to leave it running up and running for a long time, maybe a few weeks. And then you will see that it plays Pac-Man comfortably, and it will win to maximize it. And by the way, the game of the Atari console games, all the games, people have experimented with, and they have won, like accomplished superhuman capability in playing on the Atari machine. Just about any game you can throw at, give input of sequence of screens, and then this machine player will play and beat any. I'm going to close the environment and then draw the video. So here you can see it balancing comfortably, quite a bit. And then it falls off. But it did a decent job. It did. So let's go see the video one more time. See, it's balancing nicely. And ouch, it is going to go out. There we go. And it dies. So that's the concept. So it did a fabulous job compared to what other attempts that we have had up until now. And now we will discuss the idea of Markov chains and Markov decision process, which involves a little bit of drawing. So we'll go back here and draw them. So Markov decision process, it sounds crazy, but it is not. It sounds scary. What are these circles and arrows and numbers doing? But it's not scary. So if you read just at the picture, you can probably intuitively tell what's going on. Just by looking at the picture, I'll tell you how to read it. By the way, it is described here, so we don't have to read it, but I just look at the picture and read directly from the picture is what I prefer. So having said that, let's see what these S0s, S1s, and S2s and S3s are. They're states of a game that you're playing. So you begin with a given state. And then the idea is to make a move, take an action. So in that step 0, or rather state 0, we have a couple of actions we can take. There are actually 3 actions. One is this action, and this action. So 3 actions you can take in the step number 0. And those 3 actions are, you go this direction, you go that direction, or you go this direction. And the chance of you taking those are also defined here, here, and here. So there is 70% chance that you will take this direction, this one. And then when you take that direction, you will end up right here, back to where you are. 70% chance. And so in other cases, or 20%, you might take this direction. And then you land on here. Because that's a 20% probability, you might land in this spot. And so also there is a 10% probability that you land on the other spot, like here. So you go this direction and you end up here. And that's the state transition happens with this probability. This state transition happens with this probability. And this transition happens with this probability. That's how you interpret this particular state. That's a state diagram effectively, with a probability transition indicated by the number associated with the arrow. And let's go look at another example, another state. So imagine if you now landed on the other state, which is this S1, for example. If you say land on S1, so you have this chance, 20%, and you end up here. So on that state, S1, there are only 2 ways you can move, this way or this way. And so the 90% chance that you will go this way, and 10% chance you will go this way. And so it's likely that you end up here. There's a higher chance. And so you will end up here. By the way, the transition from here to here will happen only 20% of the time. 10% time you'll straight go to S3 without even visiting here. There's a less likelihood of you visiting there. Similarly, the idea of S1 traveling to S2, 90%. S1 traveling to S3 state, 10%. Once you end up here, for example, the idea is that you can go only one direction, and that is the only direction. So the probability is 100%. That means you will always come back. If you go that route, you always come back. There is no other way to go. That's 100%. You're back here. And so eventually you will end up this direction. And so you will then end up at S3, like that. And once you're here, you're done, because there is no escape route. In this example, the only route to go out is back to itself. And with a 100% chance, you're stuck here. So that's how you look at a Markov chain illustration of chance of state transitions from one to the other, to the other, to the other. And in the equilibrium here, most cases will transition and end up in this point, is how the nature of this particular Markov chain is. And this is how it is laid out in this example. So eventually, everybody or all events will get stuck here and in the S3 spot, because that's how the nature of probability and options of movement are in this particular Markov chain illustration. Having said, we'll now extend this idea to a little bit different idea called Markov decision process. That was a Markov chain. So we'll now extend this idea with a little bit of twist. And the twist is that at each step, the machine player can choose an action and the transition probability depending on the action chosen. So this is how it looks like. So let's go see the picture and see what it means to an action and a probability of that action. And there are some rewards associated with it. So we'll see that now. So if you begin here as 0, the chance of you going this way versus this way versus this way. There are three actions you can take: A0, A1, and A2. If you take any of these three actions, then the associated probability is, if you take action A1, you will end up back to S0. That's the idea here. If you take action A0, you will end up with a 70% chance you will end up accumulating 10 points and land at S0. Again, back to where you were. In the process, you accumulated 10 points, positive 10. At this action, when you take A0, there is a 30% chance that you will end up here. That's a different state. Of course, there is one more action involved, which is if you take this action, A2, then there is a 80% chance you will come back to where you were, and a 20% chance that you will reach S1. So you will eventually reach S1, or you might, iterate here and accumulate some 10 points over and over and over again. There's a high likelihood, 70% chance. You might take these actions and keep accumulating points, 10 points each, by going around like this. 70% cases. 30% cases you might reach here. And the optimization algorithm intuitively tells us that, you don't want to go iterate like this. There's no benefit to gain in this game. So you can iterate like this, A2 action over and over and over again, 80% probability, but no gain. You would rather take this action and there is some gain involved here. So you accumulate those points. So pick those 10 points and keep iterating on those. So you accumulate a lot of points that way. And you're still at the same point to begin with. So that way you can take a case and always take action A0 and keep accumulating these points and remain here. Hope perpetually. Hope. But may not be the case, because in some cases you will end up here. And so if you end up there, in that case, the scenario is that you can take only two actions. They are A0 and A2. There is no A1 action. Not available here. A1 action. So the scenario here in S1 is that you can take this action, and of course you will come back to the way you are with a guarantee, 1. And you will always keep coming back to the same point, but no benefit there, no gain involved here. If you take this action, well, you're likely to run into a problem right there. You'll run into fire, and you will accumulate a -50 as a consequence of that. And so you have to go through this fire if you take that route. But once you're here, the only action you can take is this action, which might put you back here in 10% of the cases, or might put you back here in 10% of the cases, which is going to be a problem, because the only way to escape that is through fire. You have to go through fire to come out of the S1 state. You can keep going back to where you were, so do nothing basically. Or you go through fire and maybe go to this point. When you're here, there is a chance, 80%, that you can actually accumulate lots of points as you go back to where you came from. And so from a step sequence perspective, if you want to optimize the number of hearts and minimize the number of fire that you run into, you can maximize like this. If you go this way and take fire and then come back, or iterate on this to accumulate lots of points. Or you can go like this and lose only 10 points in the process, 50 points gone, 40 points collected, 50 points gone. So you have various choices you can make. And these are probabilistic in its nature. So that's the underlying idea behind a Markov decision process, where you have to, at every state, decide whether you go this direction, go that direction, go this direction, do action A0, A1, A2. And of course, there are some trade-off associated. You get some points, lose some points, gain some points along the way. So the idea is to estimate what is the optimal state value, optimal, of any state, which is the value for a state, S. So the idea here is value for a state. You want to identify what is the optimal value of a state, like here, or here, or here. And you can calculate that using this equation, which is this equation. And its nature is recursive, meaning this item is here. It is recursive in its nature. This is a previous state. This is the next state. So based on this understanding of the Bellman optimality equation, you can estimate the value of a state, optimal state value for any given state using this method. So let's go understand what that method is. And we'll implement this because that's the basis of our algorithm, which will help us calculate the optimal state values of every state. And that's what we are trying to accomplish, is to understand what would that be. And that is your optimality equation, which helps us understand the idea that this phrase here is the transition probability, T, this one. The transition probability from S to S dash. So one state to the other. What the transition probability is, given that the action chosen is A. So for every action, you go from this state to that state. That's the probability. That's T, transition probability. Then you have this R, is the reward you get when you go from S to S prime, given the action A. So you take this action, you go from here to here, you get a reward. And you have to discount future value, state values. And so that's what this discount factor comes into play. Discount this factor. And that's the discount rate. And that's the concept behind our estimation of optimal values. And you can iterate on this algorithm because it is recursive in its nature. You can see this V and this V repeated. And so using this recursion, we can estimate the value of optimal value of a state. And that's what we want to do next. So we'll iterate that. Iteration is simple. You take the transition probability, and then put in a summation here and add the reward for a transition by this action and discount by the discount rate. And you keep doing it for all states, and you keep assigning iteratively and find the maximum reward you can get. And that's the idea behind estimated value of the state S at the kth iteration of the algorithm. You keep iterating this until you find the max value of this expression, transition probability multiplied by the reward you get now and discounted values. And you keep iterating for all state transitions, and you keep doing that. Kth iteration, K. And what we are really trying to calculate here is that this can be an infinitely long game. You can keep, if you look at the picture again here, you can keep transitioning in this picture perpetually. And so, you can keep going like this until you decide to go, until you end up going here statistically. And so it's an infinite loop. If you keep traversing this tree like this and you keep going like that. And so there's no end game here. There's no stability point like you saw before in the earlier Markov chain example. There was a stability point right there. You're stuck here. And so that is different in this example in that we have a perpetuity going on. And you will keep transitioning between state S0, S1, and S2 and keep doing it. And so it is mathematically impossible to calculate that directly unless you do the trick that we are looking at right now, which is called dynamic programming, which is what is implemented in here. And the concept is you break down a complex problem into simpler steps, into sub-steps that you can tackle iteratively. And so here is the iteration happening right here. So iterate K, K, and keep doing and doing, keep doing iteratively until you get stability and you eventually find out the max, the maximum value of a given state. And that's what we want to optimize on in our algorithm. So we want to find what actions will lead us to the best collection of points, like the heart that you saw or the fire you have to go through, like this example picture shows. Fire and hearts. You want to optimize, and that's what you want to keep doing until you get to the best possible situation, because that's the best outcome you want to accomplish. And so the idea behind this iterative algorithm, value iteration algorithm, is what you're really trying to know is the optimal state values. But then the idea behind value of a state doesn't tell us which actions you take. So the idea of there are two things here. One is the state value, and think of the other one as the action value. Action value is more important, more relevant, because it is directly transitioning into a reward or a result. That's what matters, the action you take. State value is where you are right now, is kind of useful to know. And so in the earlier algorithm up there, we calculated this, the value of a state. But what we really are after is this action value. What is the value associated with an action that I want to take? And so that calculation is called state action values. In other words, they call it Q values. That's the name chosen. And this is we have to find out the optimal Q value of a state action pair. In this state, you want to take this action and you want to optimize this value. That's the idea behind Q value. For any state diagram, you want to maximize the action value. So if I take this action versus that action, A0, A1, A2, which action gets what the value of every action is at a given state? That's what I really am interested in maximizing, not the value of the state itself, but the action value. What's the value for this, value for this, value for this on a long-term sustained game? That will tell me and guide me what action I should be taking, because that is what results in an optimal solution to the problem. So we are discussing two different entities here. We are talking about one, which is the state value, the one which is action value, also known as Q value. I don't want you to confuse the two. And so this next idea is estimating the action state pair QSA is the sum of discounted future rewards that the agent can expect on an average after it reaches the state A and chooses the action A. But before it sees the outcome of this action, assuming it acts optimally on that action, meaning it doesn't know what the future will be. It just wants to know what is the value of an action I take right now. Is it going to help or not? And what's the optimal course of action to take? And that idea is called Q value, is what you want to optimize. And the algorithm to optimize on that is very similar to the one for state value, in that what we are doing is we are also iterating similarly like before, but on Q values, we are taking a max of Q values, putting the discount factor right there. And this is your reward at a given step. And you are assigning transition probability, multiplying that right here. And you keep iterating for all states and all actions. and k iterations right there, k. And so that's what will lead us to optimizing our Q values for a state S taking action A. So you can then apply this in a Markov decision process in our earlier example. And we'll see how we can structure this Markov idea into an array, into a Python array. You will see that now. So I think it's better to have this picture on this side and compare with this on the other side. That will be better. So I think we are discussing Markov chains on the notebook, and then there's Markov decision process. And I think this is what is implemented here. I think we should just read and figure out what exactly is the implementation. Is it this or the next? I think the next one. So this is where the Q values are calculated. This is your Q learning. This is your MDP, and prior to that we have Markov chains discussion. So let's go run these guys one at a time. So the Markov chains, we are assigning transition probabilities. So let's go compare the Markov chain picture here and see how these transition probabilities are laid out in our transition actions. So let's go see that. This number is right there. 0.2, 0, and 1. So this number, then 0.2, 0.1, and there is a 0. So these transitions shows from S0 to S0 itself, to S1, to S2, to S3. As you can see, there is no transition from S0 to S2. There is none. That's why this number is 0. From S0 to S3, this transition is there, 0.1. And like that, you will fill up an array of all the probabilities of transition from state S0 to S1 to S2 to S3, and like that, from S1 to S0 to S2 to S3, and S2 to S0 to S1 to S3, and S3 to S0 to S1 to S1 to S2, like that. You will fill it up. That's the probability of transition as laid out in this Markov chain. You run some maximum steps, you define that, you print the sequence, and this is your print function, and that's what you see the sequences. And you will see the end result is always 3. And it will eventually get to 3. So that is what the steps run out. That's why in the number of 50 steps, you don't see an item output 3 at the very end, but it will come. It will absolutely come. This is a statistical random choice. And so that's what you are seeing, that most of these outputs are 3 at the end, because that's the terminal state. S3 stuck at S3. That's your concept of Markov chain implemented in Python. Let's go see the next idea, which is Markov process, decision process. The next idea here, same thing again. We are assigning and calculating our transition probabilities first. Where is that? Here. So S0, S1, S2, 3 states. So we have our transition probabilities right here, 0.7, 0.3, 0.0. So this is 0.7, 0.3, and 0.0. And like that. It is for every action you can take. So the second set of transition probabilities are 1, 0, and 0. This is for your action A1, this action. So you're still in S0. The first item is action 0. This is still in S0. The second item is action 1. And this is your action number 2. And these are all in state S0, all the actions. Next one is the state S1. The actions are 0, 1, and 0. The only action you can take in A0 is with a guarantee of 1. There is no A1 action in this state, so it's not there. That's why you have none. And then you have this action, which is 0, 0, and 1. That's a guaranteed action. That's the only action. If you go, that's the only output you, or the likelihood of you going through that is that number. And so that's why you have 0, 0, and 1. Then the third step, S2, you have no A0, no A2. That's why you have none here and none here. And for A1 action, there are 3 possibilities, this, this, and this. That's what you have laid out here. So that's your transition matrix. Now, in terms of rewards that you collect, you have this 10 plus, you have this negative 50, and you have positive 40. These are the 3 rewards here, here, and here. And that's the reward function expression in a matrix. The possible actions you can take. I'm going to clear my ink. Possible actions are, you can go from 0, 1, 2, 0, 2, and 1. So in here, these are the actions. You can go to A0, A1, A2. You can go to A0 and A2, and you can go to A1. That's the only course of action, the possible courses of action. Then you define a policy of fire, which is it's not policy of fire, it's policy fire. So it's initial step. You're defining basically these 3 functions: policy fire, policy safe, and policy random. So 0 to 1 is what the fire policy will result. Safe policy will result this, and a random policy will send a random action. So that's the action state defined in terms of policies. Then we defining a class for MDP environment, and the class itself defines these definitions. How do you initialize? How do you reset? How do you step? And that's the class definition. We'll use this class definition in the MDP environment to execute initialization, reset, and stepping. And then we define an episode. And in that episode, we define an environment based on this class. And if you have a display, when we start stepping through this, so if display step equals 10, print, else print, an action policy and action. Let me adjust this. Erasing that and adjust my screen. I think this deserves an execution. And so you can see the policies getting fired and the rewards estimated and calculated. So let's go execute this quickly. It should be quick. There we go. And so this is your policy fire, policy random, and policy safe. And at the end, you can see the rewards mean, standard deviation, minimum, maximum. So if you take the fire policy and the safe policy, you will see that it does maximize. The maximum reward you can get is 470. The maximum reward here is you can get a max of 170. The mean here is higher. The mean here is 22. The mean here is random policy is negative. And let's understand what this actually means. This idea is that you want to play safe. So you are basically doing 1, 1, 1, 1, 1, 1, 1. And what you're really trying to see is you're trying to play safe. You're going this game. Whereas the policy fire is you're actually making it go through fire and accumulate rewards like that. That's the fire policy route. So that's your Markov decision process implemented in this example. Let's now see if we can apply the concept of Q-learning here. So we will have to scroll the page again. And here is your Q-learning algorithm and implemented here. And by the way, this technique will be used to implement Pacman. So we will see that, and it will take a couple of weeks for it to train completely. And so we will actually run this. I'm planning to run it for a couple of weeks and see how it works out. I have run it once and it did not finish, and I think I ran out of patience. So it did not actually finish because of me being me, me being impatient. But I want it to run, so it will eventually run. So our idea behind this Q value iteration algorithm implemented is what we are first of all understanding in this example, and then we'll apply these techniques in an actual Pacman play example. So our idea here is that we want to watch how we play, randomly play, and then implement how do we improve our Q values by looking at something playing randomly. And so the idea here is, if you want to learn how to play golf, you will find some drunk monkey hitting a golf ball randomly, and you will eventually learn from it. That's the idea. Monkey playing golf, and you learn from it. That's the idea. We randomly let the agent play, and you gradually improve your estimates of the Q value, so you know which actions lead to better result. And then there is a slight variation to this monkey learning technique. So this is your monkey technique. There is a slight improvement that is called a greedy policy, and so that is probably also implemented here, and that's slightly better than the monkey randomly hitting a ball and you trying to learn from the monkey as to how things are and what to do and what not to do, and optimizing your Q values based on what you observe the monkey doing. And so that other method is called greedy policy method. We'll see. I think both of them are implemented here. So there are 3 states in our Markov decision process picture. Let's go put the picture on the front, on the left side. So picture here. Okay. And then number of states, of course, there are 3. So 3 states. Number of actions, S0, S1, S2. There are 3 states. Actions are A0, A1, A2. And not every state has every action. So there are 3 actions available here, but not A1 is missing here, A0, A2 are missing here. Number of steps we'll take is like 20,000. Lots of steps. We have an alpha 0.01 and a gamma of 0.99. We have an exploration policy is policy random. We randomly explore. That's the monkey playing. We are setting Q values with states and actions, the number of states and number of actions. And we are running a for loop, states and actions in enumerate possible actions, and assigning Q values to 0. Setting an MDP environment, like we have defined already ahead of time in a class function for MDP environment. And then we are stepping through the number of steps that we have here, 20,000. And for step in the number of steps, action to explore the policy and save the state, take the action, and maximize the Q value for the next state. That's the next value. And the Q values of the next state is assigned as, let's go see the math on the left side. Yeah, this one. This is your Q value algorithm. So this is the algorithm here. So Q values equal assignment 1 minus alpha. This is I think this is the greedy policy implemented. They're not doing the monkey policy. I think this is an indication of a greedy policy implemented. So that this alpha that they have decided, let me just go and cross check. I think this is not the implementation we are looking here, but the greedy implementation. So let's go check. Let's go close this. And yeah, it's the TD algorithm, temporal difference learning algorithm with a alpha introduced, which is the learning rate introduced. That is this math. So they probably skipped the notebook with this math altogether. And this particular process of iterating on Q value is not in the notebook. The notebook skips into the into the next idea of temporal difference and Q learning. So that's this implementation which implements the greedy policy right there, which is a slight improvement on the random monkey motion, or monkey trying to experiment random things, and then you figure out what's the best course of action based on what you find monkey doing. But this implementation of the notebook is the next idea. So before that, I need to go back to the book and finish off this discussion, which is how you would implement a purely random scenario. So did we do this already? Hold on. No, I did not run this portion. There is nothing in the notebook to run that. So here, if you want to run this manually, Q value iteration algorithm, you will design a Q, and the Q actions are initialized with 0. You set a discount rate and 100 iterations. Then you start iterating. You previous value of Q, you save that, and then you start taking actions. For A in possible actions, the possible actions are what you can do, or the actions defined in our Markov decision process, the picture that you saw before. It will take only certain actions are possible, certain other actions are not possible. For example, here in this state, the third state, action number 0 and 2 are missing. In this, the action number 1 is missing, like that. You can take only certain actions. If that is a possible action, then you take the summation, and this is the implementation of our algorithm mentioned ahead. So I will scroll it a little bit. This algorithm, which you see on top, is what is implemented here. Here, summation, which is this summation right there. And then we have our T as a transition probability multiplied by a bracket, rewards, discount rate multiplied by our maximum value of Q from a previous step. And that's how you will estimate the future or next value of Q. And you keep doing that for all possible actions. And then you will come up with the result. You will see that the Q values actually show you that for a discount rate of 95, the max you can accomplish if you keep doing action 0 is this. If you take action 1, this 53 is the value you can get as the max among this action. Among action 1, 53 is the best. Action 2, this is the best. Oh, sorry, no, I'm saying it wrong. So let me show you how to read this. I'm going to clear that again. So the idea is to identify in a given state. So this is your S0. Which action produces the best result? That's how you should read. So in maximum value in state number 0, which action produces the best value? You can tell that it is 21, not 20, not 16. So not these guys, but that's the max. In state number 1, the action you should take is this value, not 1.11, but 1.17, slightly better. And in state number 2, the action you should take is this action, action 1. Now let's understand what this means from that picture that we had seen before. So I'm going to erase this and compare with the picture that we have. So you will see that the max in state 0 is action 0. That's how the best action available in state 0 is action 0. If you happen to be in state 0, the best action to do is action 0. It's intuitively obvious. This is the best action. If you're here, keep doing this. A0, A0 all the time. If you can get away with it, very likely, 70% chance, you can keep accumulating points, 10 points each. Keep doing it. That's the best action in this state. The best action in this state, let's go figure out what that answer is in our estimation. You can actually tell this intuitively, but the estimation calculation shows you that the answer, the action you should take in state number 1, oops. I think I accidentally erased something for no reason. And so there it comes back. Yeah. So the action you should take in state number 1 is action 2. Let's go see why. The action you should take in state number 1 is action 2. Let's see why. Here, in this state, the action you should take happens to be this, not this. There's only 2 actions, this or that. The action that you should take, which leads you the best benefit, is actually this action, not this. This is kind of pointless action. You don't get anything, you're stuck there, same place, and you're not benefiting at all. So it's a pointless action, A0. So not doing that. That's not, you can actually tell this intuitively. If you're stuck here, this is the only course of action that makes sense. This doesn't make sense at all. Even though here there is a fire, you lose points, but still you should take that action because this is pointless action. And that is intuitively obvious also. Now, if you go back and look at the third item in our state, which we don't have to go and look at the answer in the code, but you can tell that in this state, there's only one choice, which is this. And that's the action that you should take. And then depending on this probability or that probability, you will likely to gain these 40 points if you happen to be in that direction with that probability 80% kicking in. Now, if you see and read ahead in our example here, you will see that the optimal action for each state happens to be 0 to 1, which is the action sequence that we described. Now, if you get the optimal policy for that particular MDP, the Markov decision process, if you adjust this a little bit and you decide that I will tweak my 0.95 discount rate, make it 0.90, then suddenly the optimal policy changes. And the change essentially is going to happen something like this. If you look at the picture again, and so the best course of action that will, if you transition this number 0.95 into a number that is 0.9, then the value of gaining from a future step is not much. So you're discounting the future even higher by 0.9. Earlier it was 0.95. You're still counting the future a little bit, giving it some credit. But now you discount it a little bit more. It reduces the value of future. So you are better off in this scenario. You're better off iterating like this and don't even venture that direction. So there's a risk here, and that the output it produces is actually less interesting because of the discount factor. So the discount factor that you take into account actually impacts your decision making in a Markov decision process. Having seen this, let us see. By the way, how much time we have? What, 7:30 already? Okay, I think we need at least an hour or so more. So we should get together on Thursday. Let's see if we can do it on Thursday. Confirm. Just check.
Sure. Yeah, Thursday's good.
Hold on. Let me just quickly check. That day is Thursday. I think we can do that. Yeah. So let's. I think that should be the way we finish. This should be finished by that day. I think we should take 1 or 2 hours and finish that off. So
Okay.
that should conclude. So we will get together again at December 6th at 4 o'clock, and we will proceed in this direction of understanding and this concept of temporal difference, and see how we conclude our discussion. And I leave this open to you, that you have the option to run something like a concrete example. If you're doing it, do it with me. I'm going to run this Pac-Man thing and maybe implement one more example.
Okay.
And so if you are interested, come and discuss anytime you feel like, or you have time, you just chat.
Okay.
With that, I am stopping my recording, and I'll see you Thursday at 4 o'clock.
Okay, great. Thursday at
Thank
4.
you. Thank you.